Hello everyone. Now we will talk um, about the confidence interval for mean when sigma is not known. Okay, and then we'll talk about the prediction intervals and the tolerance limits. We see that when sigma is not known, we just plug in s instead of sigma, and the resulting random variable x bar minus mu divided by s divided by root n is a t random variable. Okay, so just like we did for the case of the normal distribution, we can just write the random variable t is between minus t sub alpha over 2 and t sub alpha over 2. Okay, so the probability that t is between here and here is equal to 1 minus alpha. So instead of t, what I will do is just plug in this value. So probability that instead of this t, I will just write x bar minus mu divided by s divided by root n. Okay. And after some algebra, we will see that we have the probability that your unknown constant parameter mu the probability that moves between this value and this value is equal to 1 minus alpha. This is very similar to the previous case. Remember, instead of t, we just had z alpha over 2 here and z alpha over 2 here. Okay. So we can just write the confidence interval as follows. So if x bar and s are the mean and standard deviation of random sample, okay, then your confidence interval is given by x bar minus t alpha over 2 times s divided by root n and x bar plus t alpha over 2 s divided by root n. Okay? And t is so t alpha over 2, as you might remember, is the t value with n degrees of n minus 1 degrees of freedom, and it is an area of alpha over 2 to the right. So remember our example, we have the heads of 10 students from this class. Just find the 95% confidence interval, which means alpha is equal to 0.05, assuming that there is a follow of normal distribution. So we are not given sigma, we will just use S. In order to use the t distribution, we need this assumption, which says that, well, the heights follow a normal distribution. So we will need t alpha over 2, which is t sub 0.025 at how many degrees of freedom? V is equal to 10 minus 1, 9 degrees of freedom. Right? So remember, it was from the table, it was 2.262, okay? And hence the confidence interval is um, so just plug in the values. I have x bar as 167. This is my t value. This is the s value, the sample standard deviation, divided by the square root of n, which is root 10. If you just plug in the values, it turns out that the unknown parameter mu with what? With I am 95% sure that it's between 160 almost, let's say the exact result, 160.65 and 173.34. Okay? So assume now we know sigma is equal to 9. Okay, so we know the population parameter sigma. Now construct the confidence interval again. So what do we need? Now, since we know sigma, we can just use z, right? So we need z sub 0.025, which was, if I'm not wrong, that's 1.96, right? Right. And just write sigma instead of s, which is 9 divided by root 10, and so on and so forth. So it turns out that if you know sigma, then you can use sigma and then use the z random variable. So the resulting confidence interval is this, means between 161.4, 172.56. So if you know sigma, okay, if you know sigma, then you can just use z, right? In hypothesis testing and in confidence interval, if you don't know sigma, right? If you don't know sigma, then you will just use t, both in hypothesis testing and confidence intervals. Okay. Well, here are some notes. Well, when the population variance is known, so sigma square is known, we can rely on the central limit theorem. So this is the thing that we have just written in the previous slide, and just construct the approximate confidence interval for mu based on the normal distribution, okay? So if you know sigma, then using the central limit theorem, you can just use z and construct your confidence interval. However, when the population variance is unknown, when you don't know sigma, okay? Well, CLT does not help. And under the assumption that the distribution is nearly normal, so you need normality, but approximately normal works fine. We can use the T distribution to construct again a 1 minus alpha confidence interval for mu. Well, in many applications, provided that the population distribution is not far from symmetric. What does this mean? So if the population distribution is not something like this, or is not something like this, but it's something like, for example, this, or I don't know, a little bit skewed to the left, or a little bit skewed to the right, right? So if it is not too far away from symmetric, then a nearly bell-shaped, sorry, it's not far away from symmetric and nearly bell-shaped, okay, then we may use the T distribution to compute confidence intervals with approximate but satisfactory result. So if you don't, if they are not normal but they are not far away from symmetric, then instead of having no results at all, you can just use these approximate confidence intervals. Okay, so the next thing we will talk about is the prediction intervals. So prediction interval is, well, so up to now, we just deal with the value of mu, okay? What was mu? Mu is the what? Mu is the parameter of the population, right? So we deal about mu and say that, well, mu is in an interval, okay, this is the confidence interval. But what is mu? Mu is the average height of the students in the university. Okay, that's the average shade. That's what. So let me just plot it on the probability distribution. So if this is your distribution, mu is this part, right? This is mu. So what you're trying to do is you're just trying to set where mu is, right? So it's somewhere in between. So you just find confidence intervals and so on and so forth. However, sometimes we're interested in predicting the possible value of a single observation, okay? Single observation. So what does this mean? So just remember the difference by looking at this example. What is the probability that x bar is greater than 180? So what is this? The probability that the average of the class is taller than 180. And look at this probability, the probability that x is greater than 180. So what is this probability? It's the probability that a single student is taller than 180. Remember this? So these two are different, right? So this is the probability for a single guy. This is the probability for the average of a class, right? So up to now, we talk about the average of the population. That's fine. That's fine. But what I need is I want to make some, let's say, I want to make some inference, make some predictions about a single observation. Okay. So this is what we call a prediction interval. So before getting into the prediction interval, let's recall what we can write for any normal random variable x, with mean mu and with standard deviation sigma. Well, we can just write the following, okay? We can write the probability that x is between mu plus z alpha over 2 times sigma and mu minus z alpha over 2 times sigma. So the probability that your random variable x is between this number and this number is equal to 1 minus alpha. You can check whether this is true or not. How? When you're trying to find the probability of a normal distribution, just convert it to standard norm, okay? So what you do is just write x minus mu divided by sigma. So here I will just write mu minus z alpha over 2 times sigma minus mu, okay? Minus mu divided by sigma, right? Let me just write it like this. Smaller than, and this is smaller than, just write mu plus z alpha over 2 times sigma minus mu divided by sigma, okay? So what is this? Since x is normal, this is z, okay? And what is this? Mu cancels, then sigma cancels. This is z sub alpha over 2, and this is mu cancels, and sigma cancels. This is probability that minus z alpha over 2, z and z alpha over 2. And this is, let me just plot it, although you know it very well. So this is just plot my standard normal. This is minus z alpha over 2, okay, and this is z alpha over 2, and here I have alpha over 2 and alpha over 2. The remaining region is 1 minus alpha over 2 here. So this is alpha over 2, alpha over 2, and this is alpha over 2, and this is 1 minus what? 1 minus alpha, right? So the probability that your standard normal random variable between minus z alpha over 2 and z alpha over 2 is equal to what? 1 minus alpha, right? So we can just write this. Okay, that's great. Um, okay, let's then continue. So for example, if mu is equal to 170 and sigma is equal to 10, and just take z sub 0.05, which is equal to 1.96, okay, we have the following, right? So the probability that x is between, just plug in the values, x is between 150.4 and 189.6 is equal to 0.90. So again, what I do is I just plug in the values. Okay, I just plug in the values here up to there, and this is my result. Okay, the probability that x is between 150.4 and 189.6. This probability is equal to 0.90. So okay, so let me just ask you. Sorry. Um, okay. So let me ask you this. What does this probability mean? What does this probability mean? Well, this probability has two meanings. The first meaning is in terms of a single observation, single individual, okay, single individual, okay? And the second one is in terms of the population, okay, in terms of the population. So in terms of single population, what does this mean? This means that the probability that a guy coming into the class, his or her height, the probability that his or her height between 150.4 and 189.6 is equal to 0.90, okay? So the probability that the student's height is between these two values is equal to 0.90. Okay. So in terms of population, what does this probability mean? Well, it means that 90% of the population, okay, 90% of the population's height, 90% of the students' height is between 150.4 and 189.6. Okay, so in terms of single individual, this is a probability. In fact, this is a probability for in terms of population. It just gives a percent of the population that lies in this interval. Okay, so there are in fact two meanings for this probability. Okay, great. So, okay. So let's stop this session here. And in the next video, we will continue with the prediction interval. Okay.